Those clamps are a little far from the cut, and this material is fairly thin, but it's 4140 steel. It should hold up against this cutter, I think. Hello Internet, my name is Quinn, and this is Blondihacks. I'm working on my locomotive again this week, and I'm going to make the radius rods. What do the radius rods do? Well, stay tuned, and you'll find out. The radius rod connects from the pivot point of the combination lever along the top of the mechanism here, eventually connecting to the expansion link at the back. Of course, if you watched my wall shirts video, then you will recognize it as this blue lever running across the top here. This lever both sets the pivot point of the combination lever and allows us to change the valve hookup using the quadrant. If none of that made sense, then go watch my video on wall shirts valve gear. I'm going to make these radius rods out of this lovely piece of 4140 that I have for the purpose. Very nice free machining steel, also very strong. However, it is cold rolled, so I am going to start by normalizing it. Normalizing it is simply heating it up to annealing temperature and then letting it cool down slowly and naturally. That releases all the internal stresses put in it by the cold rolling process at the steel mill and prevents the part from warping when machining it down. This is especially important for very long, thin parts like these radius rods where that warpage would almost certainly occur. So with that normalized and cooled down, I'm ready to machine this. I'm going to do some initial operations on both radius arms at the same time. Now, these parts are virtually identical to the combination levers, and in the book, Kozo suggests the exact same order of operations. However, since we're doing the same thing again, it's an opportunity for me to try something different. I'm actually going to do the order of operations that I would have chosen if I had never seen Kozo's method. This is just from my brain, not looking at any other sources. What would I do to make these parts? It's kind of a fun exercise. It's a lot of what I like machining is figuring out an order of operations for an intricate piece. And I'll be able to compare my method with Kozo's and see if it's better or worse or the same or what. Quick check after initial machining to see that nothing has bananaed, and it has not, so the normalizing appears to have been successful. Good deal. Now you can see that this scrap is machined all the way around the outside now. I've given myself reference surfaces all the way around, and the thickness of the material has been brought to the final thickness of the radius arms. Now what I'm going to do is, on the surface plate, I'm going to mark the approximate width of one radius arm along each of the outside edges of this piece of stock. And that way I can cut these apart on the bandsaw, and I'm going to have my two radius arms both with one reference surface already on them, and machined to dimension on 3 sides. That's going to leave me with kind of a funny scrap in the middle, which, fun fact, is going to come in handy later in the process, perhaps for sad reasons. These long, thin bandsaw cuts are also where the material would absolutely warp if I had not normalized it. If you've watched this series, you know that it's taken me a while to learn this lesson, but normalizing is very important on long, skinny parts. So now I can put these two pieces in the vise and machine that final saw cut down to final dimension on this axis, and then my radius rods are brought to final finished dimension on all 4 sides. And I've also machined them to length. I can start adding features now. There are 3 holes in these radius rods for all of the various linkages that they connect to. I've done my edge finding from the end of the part, so these are all going to be relative to a valid reference surface. The only real functional detail on these pieces that matters is the distance between these holes, which is going to be correct because I'm doing it on the DRO. Everything else that we're going to do is essentially just aesthetic. These parts get drilled and reamed to 2mm. Like all the rest of the valve gear, the pins that connect it all together tend to be 2mm. Now, while in the same setup, I can do one other operation, and that's to rough cut the relief on the fronts of these parts. As you can see from the drawing in the corner of the screen, there's a very large relief along the back of most of this part. Now the final cut needs to be done with side milling in order to get the nice fillet radius on the back corner that's supposed to be there. However, side milling all this material would be very slow and cumbersome, and most importantly, very difficult to fixture. So by rough cutting it into within very close to final dimension in this setup, we can save ourselves a lot of work for the final finishing cut, which we will have to do vertically. With both pieces brought to this point, I think the next thing I'm going to do is the dog bone feature on the small end of the parts. This is a good time to do it because the parts are thinned out now, they're easy to cut, and they're going to be easy to set up on the rotary table. So as I've been doing lately with these small dog boning operations, I mark the narrowest part of the dog bone, the choke point or the throat, if you will, of the dog bone using the surface plate. And then I use a pin on the rotary table to empirically observe the angles that I need to cut to on both sides to achieve the dog bone. At this point, I figured I could do this in one cut, just plunge all the way down to my sacrificial plate and then crank around the rotary table and I should be done. These pieces are only 78 thousandths thick and this side milling depth of cut is not very much, so it should be fine. And well, there was one thing I was a little unsure about, and that was whether my clamping was close enough to the end mill, because these parts are fairly thin. And the answer is no, the clamps were not close enough to the cut. If you listen very closely in this moment, you can hear my heart breaking just a little bit. Well, that was a disaster. What happened there? Why did that happen? This should have been a light, easy cut, and it was a disaster. This is a very educational moment. I learned a lot in this moment, so let me tell you what I think has happened here. Standard right-hand helix end mills have some lifting force while they're cutting. It's a desirable effect because that lifts chips out of the cut as it goes. However, those lifting forces can be a problem on thin materials. Now you really notice this on sheet metal, for example. It's very hard to keep sheet metal from vibrating when using an end mill to cut it. And in fact, for this reason, they make left-hand helix cutters that apply downward force on the material as they cut. They're not good at clearing chips, obviously, so you can't use them on thick material, but for cutting sheet metal where you don't need to clear chips, they work great. Generally though, that lifting force is not strong enough to have to worry about. And I was not worried about it here because I have very recently cut this exact same feature on much thinner material. Look at this 1/16 steel that I'm cutting a dog bone in. No vibration, no lifting forces, no disaster. So why did this work? There is a little more support material around it, which is probably a factor, but I think the key difference is that on this thin material, I was not doing full depth of cut in one pass. And what that means is, as the cutter is going around, there is material attached to the part under the cutter. So the cutter can't lift the part up because it's being essentially held down by the end of the cutter. So as long as you do lighter cuts and don't go all the way through the material in one pass, then there's material under the cutter that keeps it from lifting and reduces your cutting forces at the same time. For the second one then, I changed my clamping arrangement so I could get a clamp as close as possible to that cutter, and I did this in multiple lighter cuts. So in addition to having less lifting forces because there's not as much material engaged with the cutter as it goes around, there's also always material under that cutter until the very final cut. And on the final cut, as you can see, there's just a little bit of material left, just a very thin wisp of material, and so there isn't enough cutting force on this final pass to create any lifting. This combination seems to have worked perfectly. The second part went great. Obviously, I had to go and then remake the first part and bring it back to this point, but this process worked really well. So I learned a lot of little lessons in that. It was painful, but I learned a whole lot about working on thinner materials and small parts. This scrapped part is mocking me from the bench, but no worry, I'm actually going to straighten it out and I can use it to practice some setups later on in the process. So who's laughing now? It's okay to talk to your parts. It's when they talk back that you should worry. At this point, I'm going to need a fixture to move forward, so I grabbed a scrap of aluminum from the bin and I machined all four outside edges of it to create nice parallel and square references for setup. That's going to be very useful because I'm going to be using this for repeatability on multiple parts. And then I also machined a little shelf in it parallel to the top and bottom of the fixture. That will allow me to set this up on parallels and be able to register the part on that little shelf and know that it's going to be parallel to the vise. Then the fixture allows me to clamp this in place with some toolmaker's clamps and find myself on the edge finder, and I can start making that side milling pass that I talked about. A couple of plunge cuts to get out to where the fillet needs to be, and then one final long, gentle side milling cut, removing just the last little bit of material left by the roughing cut, and we have our fillet in the right place, and we have our part to final dimension with a nice finish. Of course, my second clamp is about to be in the way of this final cut, so what I decided to do was get close to it, and then pause and quickly add a clamp and remove that clamp, and then resume cutting. There will be a little bit of a tool mark left where the cutter paused, but that will easily sand out when we're done. A little bit of musical clamps, and I was able to finish the cut. That worked pretty well. You'll notice I was using clamps and not using tiny screws in those holes to attach the part. I learned the hard way on the combination lever that Screws this small are not strong enough to hold against milling cutter forces. That's why I planned all of these operations to use entirely clamps for every fixture. And then I've got an end stop set up there to repeat for the next piece, and I don't have to redo my edge finding. I could have used the end of the fixture, but the fixture was too short for the parts. I had to use the material that I had to make that fixture. The next feature to do is the very long slot at the end to form a clevis. Now I could theoretically do this with a slitting saw. However, there's a lot of material sticking out, and the material that I would have to hang on to is not very thick, and I think that clevis would tend to vibrate under the very high tool pressure of a slitting saw. Instead, what I decided I would try is I'm going to set it up in my fixture thusly, and I'm going to mill that slot out vertically using a very, very tiny end mill. This is a 1/16 end mill, so that means light cuts are going to be the order of the day. That's generally the downside to this approach. It's why people use slitting saws for this kind of cut. However, I kind of don't like slitting saws, and I want to try a different method, so I'm going to try with the tiny end mill and see how this goes. Now, the main disadvantage to this method is typically efficiency. An end mill this tiny can't take very heavy cuts. So imagine if we're doing 10 thou depth of cut here, this part is 200 thou thick, that's 20 passes times 2 parts, 40 passes. That's quite a lot of time. And you also have to feed slowly, because if you feed too quickly, you're going to snap that end mill. I experimented here with feeds and speeds, and I found that at 2500 RPM, I could get a 25 thousandths depth of cut pretty comfortably. The end mill seemed happy there, and so I rolled with that. Lots of lubrication, keep the chips clear, and this seemed to be cutting really, really well. Now, the other limitation, though, of tiny end mills is that they don't have a lot of reach. Cut depth limit is the other reason people tend to use slitting saws for this kind of thing. When end mills are this tiny, you really can't expect much more than twice the diameter of the end mill in flute length. So this is a 1/16 end mill, and it has 1/8 of an inch of flutes. Now, luckily for me, that gets me more than halfway through the part. So I can do 5 passes from one side, and then expect to flip the part over and finish the cut from the other side. Before I do that, though, I'm going to take another couple of side milling cuts at full depth on the front and back of the part, because the slot I need is a little bit wider than this end mill. That seemed to go just fine as well. This little cutter seems to be doing okay. That's looking good. I've made it more than halfway through the part. I can't just flip it over in this fixture, however, because of course the part is not symmetrical on that axis. If I flip it over, there's no way to hang it on to it in this fixture. So I'll need to flip the fixture around and do it on the back. Before I do that, though, I'll bring in the other part and bring it to this same point. I'm using the end of the fixture to repeat in this case because I only need the left edge of the part. Doesn't matter if my fixture plate is too short. I cut the second one the same way. Communicating scale to you in these videos is a constant challenge. I frequently show you a quarter in the hopes that it'll give you a sense of how small some of this stuff actually is, such as that tiny end mill. I'm not sure if it helps, but take my word for it, this end mill is tiny. From normal viewing distance, it almost looks like a sewing needle. It's that small. However, as you can see, I've flipped the part around, set up the part on the back of the fixture. I had to redo my edge finding, of course, because everything's moved, but that didn't take too long. And I was able to do a couple of passes from the back and finish out the slot. After I'd done the initial center slot cut, now it was time to once again move the part forward and back and widen out the slot. I started by moving the table forward to side mill the back of that slot a little bit wider. However, something terrible happened here. Watch this. Ouch. Let's look at that again in slow motion so you can see what actually happened. As the cutter engaged with the end of that clevis, it snagged it and forced it inward, and then the cutter kind of snagged the material and cut a chunk out of it. The reason that happened is because of the rotation of the cutter. As it engaged with the front edge of that clevis, the cutter, if you can imagine the left side of it traveling inward and to the right on your screen, you can see how it would grab that fork and pull it across the gap to the right. Because that material is fairly thin, it wasn't strong enough to resist those cutting forces on its own. My workaround for this was to move the cutter into the slot while stationary, then start up the mill, then translate out, then do my side milling pass, effectively leaving a little bit of material right at the outside edge of the clevis that is not cut, but I can finish that out with a file at the end. Possibly also cutting the other way, doing a climb milling pass on the back, might have prevented that problem as well, but this point I was a little gun shy to try that, so I just did the filing instead. On the other side of the part, it's fine because the part's up against the fixture and the cutter flute rotation in that case is not tending to pull the part inward. That worked fine though. As you can see, that little boo-boo took a little nick out of one side of the clevis, but I can orient that on the locomotive so that it's pointing downwards and you won't be able to see it. The part is otherwise totally intact, no harm done. It's certainly not worth scrapping the part for that little mistake. Once again, I've learned a very valuable lesson on minding the effects of cutter rotation on very thin parts. Another fun fact, I obliterated 2 of these tiny end mills doing those operations. On the right are the first 2 end mills that I used. Each of them survived exactly 5 passes in that material before giving up the ghost. They were still cutting okay right to the end, but they were starting to make funny noises, and as you can see, they are completely destroyed. I was using appropriate speeds and feeds and lots of lubricant, yet somehow those 2 cutters just burned themselves to nothing. Now, those cutters are of dubious origin. I think they might just be cheapo high-speed steel ones from who knows where. The cutter on the left that I finished with is a solid carbide Niagara cutter of known origin, and that one finished the other 10 passes on those 2 parts and still looks brand new at the end. So, as I always say, hashtag not sponsored, but don't buy cheap end mills. It's never worth it. The next feature to do are the delicate tapers along the sides of the bottoms of these parts. So I'm going to lay this out and mill to that line, same as I did with the combination levers. Now you may recall on those I mused that the taper was 1.5 degrees, hardly seemed worth cutting such a slight taper. Well, the taper on these parts is 1/4 of a degree. Talk about hardly worth cutting. However, I kind of have to cut them now because of the dog bone feature. If I don't, there's just a weird scallop at the end of these parts. So as slight as this taper is, I do kind of have to cut it now. I did it the same way as before, lined up my layout line with some parallels on the vise, and then milled down depth of cut wise until I reached the bottom of that choke point on the dog bone, and cut all the way across, and the taper should end up roughly at the bottom of that clevis if I did everything right. Of course, I never do everything right, so there's always a little bit of massaging of the shape of these aesthetic, delicate features on the die filer at the end. I've certainly learned to enjoy my die filer, that's for sure. It's such a great tool for this kind of massaging and blending of features that were done on the machine tools. It's really very difficult to create these complex organic shapes on a machine tool and not have any kind of discontinuities or tool marks or start and stop marks or anything like that anywhere on the part. Especially at this size where everything is so small that you can hardly see what the machine tools are doing. The final feature is to round the ends of the clevis, so I knocked out a couple of filing buttons for this, same as you saw me make in the previous video in this series. Filing buttons seemed like the way to go here because of the clevis. I really couldn't do a cut like this on the rotary table because of those lifting forces again, and I can't do it on my belt sander fixture because the belt pushes downward on the part and it would tend to close up the clevis. However, I could easily clamp some filing buttons around it with a little gauge pin in there to hold the clevis apart and file my way to victory. Honestly, the more I use filing buttons, the more I enjoy them. They really work extremely well. They're pretty idiot-proof. They only take maybe 45 minutes to make a set of them. You harden them, you leave them in your drawer for next time. Next time you have a similar radius to do, you'll have them ready, and the results are pretty consistently nice. It's a very low-risk way to do a feature like this. Whereas doing this on the rotary table, if you make any tiny mistake, you have a good chance of scrapping the part. But I think those turned out really nice. I'm pretty pleased with those. Off camera, of course, I did the usual sanding and Scotch-Briting to remove tool marks and give everything a nice finish. Let's see how they do on the locomotive. All the brass screws you see here in the valve gear are just temporary and undersized. Everything's a little sloppy, but there's going to be a set of specialty pins and clips and things that will be made to hold all of this together, but the brass screws just allow me to mock it up so that I can see how it's looking and you can get a vague sense of how it's going to work. Now, obviously, I can't really chooch it properly because until the radius arm is connected to the expansion link, it's not properly controlling the fulcrum of the combination lever, so you don't really get the proper effect. However, if I sort of hold the radius arm in position up against the motion bracket, then you can kind of see the constant lead being applied to the valve. And again, if you watched my wall shirts video, then you know that's what the combination lever is doing, is maintaining valve lead. So this would be simulating zero gear hookup effectively. So, you can see a tiny bit of valve movement there, but things are starting to happen. Things are starting to come together. It's going to get very exciting very soon. A couple more parts and we'll be able to see some genuine valve movement coming out of this valve gear. It's also pretty cool how the radius arm goes through this slot in the motion bracket, and that all seems to line up perfectly, so I guess I did something right on those motion brackets. Good to find that out now after everything's assembled and powder coated. How then did my method compare to Kozo's for the same part? I would say my method was a little bit slower, but it was simpler and lower risk. Each setup was fairly simple, even though there were more setups and I had to do everything twice. So I would say on balance, I would probably do it my way again, but Kozo's method is also extremely valid and also worked well. Thank you very much for watching. I hope you've enjoyed this. Thanks to my patrons for making all this happen, and I will see you next time.